Hi guys, welcome to this video. In this video, you're going to talk about linkage, a problem of linkage. So on the screen, we have a question which talks about linkage, solar linkage. Linkage was introduced or brought about by uh, Thomas Morgan, and linkage is known to be one of the greatest deviations from Mendelian inheritance, especially the law of independent assortment, which says that alleles tend to sort independently from gametes. Right. So Thomas, in his findings, realized that uh, genes are which are located along the chromosomes. Okay, we have several genes on one chromosomal arm. We can have a lot of genes, and they are located in the low side. Right. So we realize that uh, how close or far the genes are will determine whether they are going to be inherited together or they were sorted independently from gametes and later recombined in the presence of recombination. Right. So um, with linkage problem, we're going to determine how far or close these genes are to make conclusions. Right. So with this problem, the question says that the following gametes are shown in the table below were obtained from a 3-point test course in an attempt to check if the gametes A, B, and C were linked. Actually, that is going to be genes, right? Genes, I mean, gene A, B, let's see how linked they were, right? So, um, the gametes, the first question goes this way. What are the parental gametes in the table? What is the gametes produced as a single crossover between gene A and B and then between gene B and C? And also, what is the gametes produced as a result of double crossover events? What is the recombination frequency between A and B and between B and C? That is the genes are. What is the expected frequency of the double crossover products? What is the expected number of double cross products? What is the value of coefficient of coincidence for the test cross data in the table? And what is the interference value? Alright, so those are our questions, and then this are our table. So with the table, we have the gametes in one column and the observed numbers of those gametes in another column. So um, these are the gametes, different forms of them. Uh, um, because we have about three genes. To find the number of gametes that be formed after recombination. So when in meiosis, to find the number of gametes, we use the formula 2 to the power n, right? So that becomes 2 to the power 3 here. In this case, you get 8 actually. So we're going to get 8 gametes. So when I count the number of gametes here, that will be equal to 8. Okay, so with these gametes, we will definitely have parental gametes. That is the gametes, right, from the parents. So the parental gametes usually are called non-recombinant gametes, right? Those gametes were not formed from recombination. So, um, for instance, if you have this, the this one chromosomal arm is actually one chromosomal arm, right? So on the chromosomal arm, we have this gene A, which have every gene has two different forms, A and then B. I mean capital A and then small a. Those forms we call them the alleles, right? So the gene B also has capital B, which is the dominant allele, and then the small b with the recessive allele. And then the same applies to C. So at every loci, we have different genes and then also different forms of the same kind of gene. Right. So from this, we can see that since there's not going to be any crossing over and no recombination, the parental gametes remains capital A, capital B, capital C for one parent, and then the other is small a, small b, small c for the other gametes. Right, so that is why at the parental gametes we have capital A, B, C, and a small ABC as the parental gametes. They didn't undergo any crossing over, not talk of recombination. Alright, so the second question, we are supposed to calculate, determine the gametes produced as a single cross between gene A and B. Alright, so from this illustration, alright, so the genes crossing over is occurring between gene A and B. So over here, the cross between this means that at the extreme side, the A and the capital A and the small a will interchange positions. So the small a goes up and the capital A comes down. So when the small a goes up, it recombines with capital B, capital C, which are not moving. Right? So we get small a, capital B, capital C for one gamete. And then when the capital A comes down, it combines with small b, small c. Then you get capital A, small b, small c as the other gamete. So when the single crossover product, when the single crossing over occurs between gene A and B, the gametes to be formed are small a, capital B, capital C, and then capital A, small b, small c. So that is how we go about it. And then the same thing applies here. The gamete produced as a result of single crossover event between gene B and C. So this time it's between the B and the C, right? So that is why we have the cross between the B and the C. And so the crossing occurs at the extreme, all right? I said it earlier, it occurs at the extreme. So the small c goes up and combines with capital A, capital B. So you get capital A, capital B, small c. And then the capital C comes down and then it combines with small a, small b. So you get small a, small b, capital C as the gametes. All right, so this is how you go about it. Then what about the double crossover? What if there's crossing over occurring between A and B and C at the same time? All right, so from the Mendelian law, the law of independent assortment, whatever is happening between gene A and B is independent of what's happening between gene B and C. So there's independence. If there's independence, then you have to calculate or determine what's going on here, and then what's going on here, then we multiply, right? We find that kind of independence. But if there were supposed to be mutually exclusive events, then in that case, um, gene A and B crossing over cannot occur between gene A and B when it's occurring between gene B and C. The same applies for the vice versa. So since independence, both are occurring at the same time. So if both occurs at the same time, it means capital A will come down, small a will go up, and then capital C will come down, small c goes up. So if the small a goes up and the small c also go up, it forms small a, capital B, small c as one gamete. And then the capital A and the capital C also come down at the same time. It forms capital A, small b, capital C as one gamete. Or we also say that for double crossover, we just interchange the middle gene, that is a gene B in this case. So we interchange the alleles, right? So the capital B comes down, the small b goes up. We maintain the position of the other gametes or the alleles. So capital A remains its position, retains in position. The same applies to C. All right, so that gives us capital A, small b, capital C, and then the small a, capital B, um, capital, um, small a, capital B, small c. All right, so those are the gametes for the double crossover unit. All right, so after getting the gametes, what's next? We want to calculate the recombinant frequency, right? The recombinant frequency, and we know this frequency, uh, we want to compare, right? How much of the recombinants were formed, and then we compare it to the total gametes. Okay, so the recombinant gametes, their number, we divide it by total uh, number of the gametes. Alright, so the recombinant frequency is given by number of recombinants divided by total frequency. Alright, so um, to calculate the recombinant frequency between gene A and gene B, we have to look at the gametes that were formed as a result of recombination between A and B. Alright, so recombinant gametes were what? Small a. So if you go back to the table, we go back here to our number 2 where we had the single crossover. we realize that the gametes that were formed were small a, capital B, capital C, and capital A, small b, small c. So these are the two gametes that were formed, right, as a result of recombination between, a crossing over between A and B. But then you realize that even in the double crossover, the the same thing was happening over here between A and B. There's still crossing over that was happening over here. So to calculate the recombinant frequency, we will include the double crossing over gamete as well, right? So that is why we have the double crossing over gametes over here. The small a, capital B, small c, and the capital A, small b, capital C. Right, so you are going to get four gametes in all. Then you add their observed numbers. So capital small a, capital B, capital C, the number plus all the others plus the double crossover, this one plus 25. Then you divide by total frequency, number of the uh, total number of gametes, all right? So in this case, it's 1512. So you end up getting 0.209, which in percentage will be this times 100. That will be 20.9%, right? So you get 20.9%. Usually, the linkage or the linkage distance is measured in centimorgan, or is the cm, or it's not centimeters, it's actually centimorgan. All right, so that gives us 20.9 centimorgan. Okay, you can leave your answer in percentage, but the appropriate unit is centimorgan. Then the same thing applies for this one, the recombinant frequency between B and C. So you consider the single products, the single gamete that were formed as a result of recombination between B and C, and as well as the double crossover products. So always don't forget the double crossover products, because the same thing happened in the double crossover products. So over here, the double crossover products between gene B and C, there was still crossing over that was happening when we're looking out for the double crossover. So you include that in your calculation. So over here, we have that stuff as part of our calculation. So 167 represents the capital A, capital B, small c. So you go back to the table, capital A, capital B, small c is 167, right? Then the other one, that is the small a, small b, capital C, right? That is the capital A, small b, small c, right? So you look for this number as well from the table. That is uh, mm, actually the other gametes from here is small a, small b, capital C for the recombinant between B and C. Alright, so the capital A, capital B, small c, and then small a, small b, capital C. You look out for their numbers in the table, and that will be 167 and 181 respectively. Then the double crossover 31 and 25. Don't forget, we add up, you divide by 1512. Total number of recombinant, total number of gametes. Alright, so you get, in this case, you get 0.2672. That is going to be 26.72%. That is when you multiply the 100 by 0.2672. So in terms of centimorgan, you just take off the percentage and put in centimorgan. You get 26.72 centimorgan as our recombinant frequency between gene B and C. Alright, so the next question, what is the expected frequency of double crossover products? Alright, so uh, we already know the observed frequency, the observed number of double crossover. That is the 31 and the 25, right? But then, how do we calculate the expected frequency? How do we calculate the expected frequency? The expected frequency, if you look at this place, for instance, over here, before we had our double crossover products, there was a crossing over that occurred between gene A and B, and also another one occurred between gene B and C. So you consider the frequency of the recombinant gametes, okay, the recombinants, okay, the frequency of the recombinant gamete that were formed when there was crossing over between A and B, and also you consider that was gotten when the crossing over occurred between B and C. So since it's two independent events, we multiply the frequencies, right? So what's happening here is independent of what's happening here, and with independent events we multiply, right? But then if it has been mutually exclusive, we add it. It's either this or this. But then they are occurring together. So this and this. That is the single crossing over products that occur between A and B and the single crossing over product that occur between B and C. Right. So two independent events, you multiply their frequencies. So you multiply the 0.209 by 0.2672. So that is what we had here. We did this exercise for the same thing. We had 0.05580. And so in percentage, you multiply 100 by that, you get 5.58%. So in centimorgan, just take off this percentage, you have 5.58 centimorgan. All right, so we've gotten the expected frequency, right? That is the expected frequency. To get the expected number, you just multiply the frequency, the expected frequency by total number of gametes. All right. So the expected frequency was calculated at 0.0558. So you multiply that by total number of gametes in the table, which gave us 1512. So you get 84.37. And so since gametes, we can have decimal number for gametes. You approximate that to the nearest whole number. You end up getting 84. So in the next question, you have to calculate the coefficient of coincidence. For coincidence, you have to understand that is a measure of interference in the formation of the chromosomal crossovers during meiosis. So, the chromosomes will line up and then exchange their genetic material in the process of crossing over. All right. And then we realize that there's some kind of interference that occurs. The interference is when there's crossing over occurring at one point. Um, one cannot crossing over cannot occur at any other points on the same chromosome. So that is interference, and the coincidence measures that. Right. So the coincidence is measured by dividing the observed number of double crossover products by the expected number of double crossover products. So the observed number is what's in the table. So all numbers in the table are observed values. So we have 31 for, so if you go back to the table, you have 31 for the observed value of 1 and then the 25 for the other. So the capital A, small b, capital C, and the small a, capital B, small c. We realize that those are the total crossover products. So they have observed values were 31, 25. So we add them, we get the observed values. So sorry for that. So you end up getting um that is going to be 56 divided by the expected number, which was 84 as calculated earlier. So you end up getting 0.67 as the coefficient of coincidence. All right, to calculate interference, you just take out the coincidence from 1, right? You take out the coincidence from 1, you get 0.33. That is the interference. Okay, so the only way we can have a coefficient, interference of 0 is when the coincidence is exactly 1, and we can have several ways of interpreting it. All right, so that is the how can we come solve the values of these parameters given this question. All right, I think this is very self-explanatory, and then you could solve more examples on this. And then if you have not yet subscribed to my channel, um, I will encourage you to do so and tap on the notification button to get notified whenever a new videos are uploaded on my channel. All right, thank you so much.